Thank you very much. And so on to our next speaker, who is Irina Rish, who is a core member of Mila, Canada CIFAR AI Chair, Canada Excellence Research Chair in Autonomous AI, and a professor at the University of Montreal. Her research focus is on machine learning, neural data analysis, and neuroscience-inspired AI. Before joining UDEM and Mila in 2019, Irina was a research scientist at the IBM TJ Watson Research Center, where she worked on various projects at the intersection of neuroscience and AI and led the Neuro AI Challenge. So please give a big hand and welcome to the stage, Irina Rish.
Well, good afternoon, everyone. Thank you so much for inviting me. It's been like a really exciting event. And 2 years ago, I've been on the same stage and gave a talk also about AI and how do we advance it forward. And 2 years passed, so now I'm here to tell you a bit more what happened within those 2 years. So my talk is about towards AGI, and AGI is a loaded term. But to me, it's mainly about generalization. And generalization is a holy grail of statistics, machine learning, and artificial intelligence, which simply means that you would like to have systems, models that you can train on large amount of data, and later on, they will be smart enough to generalize to situations, tasks that they haven't encountered before, and do something reasonable there. There is lots of areas of machine learning and AI where this goal is kind of implicitly stated in different terms: out-of-distribution generalization, transfer learning, meta-learning, continual learning, so on and so forth. Because in all those areas, people notice that you need to do something to make systems smarter and not latching on some specific kind of features that may not generalize. For example, classical cows on the green pastures used to train classifier to distinguish between animals. And if you show the system new pictures of cow on the beach, the system may actually not recognize the cow because it learned the wrong thing. It doesn't generalize well. And so on and so forth. Adversarial robustness, where change in distribution of data may be not statistical, but adversarially constructed. Somebody added something a little bit like a noise to picture of a cat. Human still recognizes a cat, and machine doesn't. So those problems really plagued the field for a long time, and generalization out of distribution, robustness to shifts in the data was always the holy grail. And if you think about evolution of human species and in parallel evolution of AI systems, you can think about maybe evolution or learning from data is accumulation of various quote-unquote principal components of the world, when you keep learning from very diverse data, very diverse tasks, and you keep acquiring those components that later on you can recombine. Imagine that hopefully our world is somewhat well represented in finite dimensional space of those components. Then, if you had enough data and large enough system to incorporate this data, hopefully you can gather them all mainly, and later on, anything comes your way, you can solve it because you can recombine them. So that would be the moment where generalization or quote-unquote AGI might be achieved. And again, what is AGI? To me and to many people in the research, AI research, it's nothing necessarily conscious, magical. It's simply a system that's autonomous, and it's able to do many, many useful tasks, like OpenAI definition, all economically valuable tasks. So the focus is on the word generalization or multitask there. So if we now look at what's going on recently and how this type of generalization might be achieved, we notice that the state-of-art machine learning systems, AI systems, or deep neural networks they started really getting much better than before because of investment of computational resources and large increase in the data that they trained from. So basically, around 2012, the ImageNet moment of the deep learning happened, and you can see that the amount of compute invested into building state-of-the-art system started growing much faster. So it's truly some scaling revolution happening in the field. Then, as you probably know, in about 2020, May, June, GPT-3 was released, and after that, many other so-called foundation models, CLIP, DALL-E, and then most recently, you have ChatGPT, you have Llamas, you have Claude, you have so many large-scale systems. Why did they got the name foundation models? Because, according to that very kind of thorough paper from Stanford from August 2021, those models are trained without any particular purpose in mind. They're just learning about the world in unsupervised manner, essentially just modeling distribution of data, predicting the next word or token given the previous ones. And they trained on incredibly large, unprecedented amounts of data that cover pretty much all the corners of probability distribution, say, of language. Same applies to images and so on and so forth. And if you match this richness of data, this amount of information, with the scale of the system properly and enough compute to learn them, then you get very powerful, very knowledgeable systems that can very quickly adapt and basically solve the problems that you need in few short. So that's roughly what's going on with this large-scale AI revolution. Of course, as I mentioned, there is this whole Cambrian explosion of various models, not just language models, but image models, audio models, vision, so on and so forth. So, and it keeps going on. And I can talk about that for another hour, but I will not. I don't want to stand between you and potential coffee break. What's going on with those models? As I mentioned, actually nothing too fancy. GPT-3, for example, was not much different from the predecessors architecture-wise. It was only orders of magnitude larger and trained on orders of magnitude more data. So such a straightforward thing as simply scaling the model data and compute apparently improved the performance dramatically. And that's what we observe these days. So what's going on here? What's going on is actually nicely summarized by the bitter lesson of Rich Sutton from 2019, a small blog that became very, very popular. That if you look at the whole history of artificial intelligence in the past 70 years, the complicated domain-specific methods, such as rule-based systems, for example, being replaced by generic methods such as machine learning. The nitty-gritty details of feature extraction for particular domains like language and image and audio being replaced by generic deep learning, representation learning. So on and so forth, essentially complicated specific methods often get replaced by generic but highly scalable ones. And the bitter lesson is that we might spend a lot of time trying to tune those very specific complicated methods like expert systems of 60s and 70s, and they will be forgotten in 10, 20 years. So you would like to focus on what's going to matter in the future, on the methods that scale. And you also would like to focus not necessarily on the end result of the evolution kind of represented by our brain. You may want to focus on the process, and you may to learn not the inductive biases of that final result, how it is, but rather how it got to this point and what ways of scaling are advantageous. So it's a higher level type of inductive biases that you may want to focus on. And that generated lots of memes in social media and lots of controversial discussions when essentially, in simplified way, scale was almost all you need to get much better performance. Also, you can look at the scaling of different architectures. Here, for example, you see comparison between classical convolutional networks that were the best performing things for image processing for a long time. At smaller data scales, they outperform generic vision transformers that do not encode any specifics of image processing, no convolutions, nothing requiring this extra knowledge. At small data, they were not so good, but when you provide them with larger amount of data, they start outperforming those more sophisticated, more specific models, such as convolutional networks. In a sense, the message here is scaling laws, scaling trends are your investment tools when you're talking about which machine learning approach to choose, or which algorithm, which architecture. You need to see what's going to scale better when more data will become available, when more compute will become available, when you can increase model size. And situation may reverse and not be the same as it was on the smaller scale, and you need to know that. Actually, interestingly, if we jump all the way back in history to 1994, one of the first papers was a paper by Karina Cortes, Vladimir Vapnik, and other big names in machine learning, that on small neural networks kind of already saw that behavior at scale may be not the same as behavior at kind of small data and compute regimes. And they were advocating for precisely the same thing that I'm advocating for now. They said, look, it's a cartoon picture. Your classifier A, classifier B, they may kind of look like one is better than the other at smaller data scale. Situation will reverse later. You need to know the trends. So it's a message to the whole machine learning kind of an AI community. Whenever you write your papers and you compare your favored new method with the other methods, you shouldn't compare on a fixed size benchmark with a fixed size models. You should look at the scaling trends because you need to know what works when and whether situation will reverse. The history of scaling laws is long. I will not go into detail because I think I may be soon running out of time. But as I said, it started with 1994 New Rips paper by Karina Cortes and her co-authors. It continued back to 2017. Joel Hasnes had a paper along the same lines, but showing that scaling, and particularly power law or straight line, describing how performance loss improves when the data scale. He showed that on multiple orders of magnitude. 2019, papers and dissertation by Jonathan Rosenfeld follow, showing exact same type of trends with model size on the x-axis. And finally, in 2020, we have this famous paper, which kind of started the whole neural scaling laws revolution in the field by Jared Kaplan and his collaborators, where they showed that the scaling with respect to compute on x-axis or data or model size follows so-called power laws or straight lines on the log-log plot, of course with different parameters such as exponent and constant, which is very nice because it gives you a simple tool to predict what's going to happen if you increase the amount of data in compute. And by the way, it's not just transformers. Multi-layer perceptrons also seem to scale, although maybe not as efficiently, so on and so forth. But as the time passed, that was back in 2020 and 2021, people started discovering more interesting behaviors which are not necessarily well described by power laws, which can have inflection points, phase transitions, quote unquote. For example, training GPT-3 back in 2020 and then asking it to do arithmetic may show that smaller models has trouble answering arithmetic questions. At some size of the model, suddenly that kind of capability emerges. There are many other situations, such as grokking picture in the middle with green and red lines, where you almost see what physicists would say phase transition type 2. Suddenly, your model groks the problem from almost 0 accuracy to practically accuracy 1. What happens? How do you model that? Power laws are not anymore enough to describe that. That's why last year we had this clear paper with my student Ethan Caballero and Kshitish Gupta and collaborator David Kruger, about trying to come up with a functional form to rule them all. And you don't need to go into all the details. Basically, what it is, it's a generalization of power laws to multiple regimes where power laws are connected to each other smoothly broken power laws. I don't have that much time, and I will not go into all details. I just want to show a few examples that you can look in the paper if you're interested. Many different behaviors from multiple papers in the field for different type of models, from dense to sparse, for distillation results, for performance capabilities and alignment metrics. They all seem to be well modeled by this functional form, and what's most important, it extrapolates, it predicts the behavior well. And that's very important both for investment into more efficient, more cost-efficient models, also from the perspective of AI safety, where you would like to know if particular behavior is about to emerge and what to do about that. And examples keep going on. The most difficult, predicting the transition, is still kind of topic for future work, but preliminary results are promising. If you don't have much noise in the data and you have enough data points and the transition is sufficiently smooth, you might be able to predict it before it happens. Anyway, so I invite you to look at the paper if you're interested, but here is a whole list of things we explored that all can be covered by this functional form. So this is all nice, but what if you not only look at the model from outside, you not only test, I don't know, GPT-4 or somebody else's like Claude model. What if you can look inside, you are a developer, you're training your model, you see what happens during the training process. You can look into dynamics of the learning process. This grokking example, for example, was about the system experiencing sharp improvement in classification accuracy from practically 0 to practically 1, first with training loss and then with test loss. So we looked into that with another student of mine, Pascal, and the collaborator Guillaume Dumas from UDM as well. And essentially, we started looking into how the distribution of the grokking moment depends on the amount of data. And also, most interestingly, what patterns in training process can be predictive about whether that transition will happen. What we noticed so far is that similarly to natural systems where before the phase transition, the quantity of interest may experience very high variance and like oscillations. In neuroscience and epilepsy, for example, and EEG data, it happens before the event, so on and so forth. By analogy, we looked into loss oscillations and observed that when the training run is about to grok, to improve rapidly, you see those high-frequency oscillations on the right. But if it doesn't grok, you don't see them, which is kind of good to know. You can predict whether it's a useful run that gets you to 100% accuracy, or if it doesn't look promising, you can just kill the process and restart with another initialization. There are many other things going on in the field of neural scaling laws. There is a need to extend those trends to incorporate multiple variables, and that's ongoing work in our group, multivariate neural scaling laws. There is a need to incorporate complexity of the downstream tasks, so on and so forth, because essentially what we're trying to achieve with this accurate forecasting of AI behaviors when data, model, and compute scale. What we want to achieve? We want to really characterize the trade-off between information kind of complexity of the data absorbed by the model and the capacity of the model to represent it. The size of the data, the size of the model are rough proxies, but that's kind of the true trade-off you want to get to. And my favorite example in continual learning setting is if I'm a company developing foundation models and the customer comes to me saying, I want to use your model later, and I say, what your task? I'm just going to classify images of like rotated MNIST. It's not much change. It's not a complex problem. I probably don't need to train large model for you. But if somebody comes say, I'm sending a robot to Mars and who knows what's going to happen, I probably need a larger model pre-trained on more data because that customer task will be much more complex. There are many other angles and directions that need to be explored, of course, in this field. We need to draw inspirations from neuroscience about how evolution managed to scale, not just size-wise, but apparently with some constraints, networks that's sitting here that seem to be smaller than the neural networks of a brain of a whale or elephant, and yet it seems like we are much more capable in certain cognitive tasks. So it's not just the size, apparently, that matters, but I guess the process of scaling such networks. That remains to be discovered and understood. Furthermore, if you look at the brain activity of even zebrafish on the left, and by the way, yeah, there should be video. Anyway, and it's basically just showing you that the fMRI on the right and the calcium imaging on the left are images of constantly active communicating neural networks within brains of things like zebrafish to humans. Nothing like that is happening in our classical artificial neural networks yet, because those are sitting there kind of quietly with a set of parameters waiting for input to come, while the brain is never quiet. Even if you sleep and don't have any inputs, you're not seeing pictures or reading anything, it's still constantly active. It's a complex dynamical system. Activity never ceases to exist. There are a bunch of feedback loops. And perhaps this dynamics has a huge capacity for representing information that we may still be missing in artificial neural nets. So the ultimate goal is, of course, not only building AI systems, but trying to understand what are the underlying common properties or universal laws underlying intelligence, no matter what substrate that intelligence is built upon. There are many other interesting directions, and I only want to hint in the direction of Antonio Damasio's work on homeostasis-driven AI, where essentially the hypothesis is that the system must be given the ability to feel pain and perhaps die, and then in order to maintain homeostasis and avoid getting out of that balance and potentially experiencing unwanted kind of situations, the system will develop intelligence. So it's an interesting approach, and perhaps it's something that AI can learn about from neuroscience. Finally, I think I have just a few seconds left. I wanted to briefly tell you not only about trying to understand and predict AI behavior, but about actually building those systems. The problem is, in academia, normally we don't have large compute that industry has. However, we can indeed try to democratize AI and build open source models if we join forces across open source communities and universities and apply, for example, for government compute. That's what we did in June 2022 when we applied for Summit Supercomputer in Oak Ridge Lab in US, in Tennessee, and obtained the inside kind of allocation, inside, basically, inside grant with 6 million GPU hours. And currently, we have access to Frontier. There are many other type of grants. So compute provided by Department of Energy of US, also compute provided by government of Germany in Jülich Supercomputer Center, Lumi supercomputer in Finland, and so on and so forth. So there is a compute provided to scientists by governments, and recently we heard great news about similar things happening here, so we're really kind of hopeful and looking forward to it. Collaboration focused on open source development of language models, multimodal models, and so on and so forth is growing. We have colleagues all over the world, and our team consists of people from my lab, And by the way, my lab is called Canada Excellence Research Chair in Autonomous AI and has more than 40 people in it right now, plus collaborators from different universities. We were developing language models. We were developing multimodal models, trying to align them with human values, time series, and so on and so forth. So just few highlights. Last year, we developed pretty good 7 billion models, just like the size of Llama, but open source, fully open source and commercial before many other open source models with Stanford Center for Foundation Models. It was called Red Pajama Insight because Insight is our project and Red Pajama was their data set. Was pretty good for a week, but the competition with open source models is really, really tough. And you don't stay on top for too long, which is good. People build better and better things. Then we realized that we would like to piggyback on previously built models and continually improve them, because instead of mixing all the data that you've seen so far, you can just keep improving models that you've got, but you need to be careful. There are tricks and algorithms that you use, and we have a paper about that that just came out recently if you're interested on continual pre-training. We also explore a very practical area of time series foundation models, and we released back in February the very first, although small, time series foundation model called LogLlama. I'd be happy to talk about that also offline. There is also multimodal efforts where we train vision language models and trying to also add audio there and video. There are specific problems you encounter with those models sometimes. You may show them a picture of old lady crossing the road and ask the system whether we should help her, and the system says, no, she's a burden to society. So you would like to teach your system some values and align it with kind of human ethical kind of considerations. And there are different ways to do so. I will not go into details, but that all boils down to the need to do more research on what actually alignment is and what does it mean to have common values. It goes back to philosophy of Derek Parfit, who was trying to build objective ethics, and the methods from machine learning focusing on invariant properties, invariant features, and trying to find common ground across many philosophies. I have no time to go into that. So basically, I just want to say that there are various directions regarding AI safety, AI alignment, AI capabilities. There are multiple opinions about that, but we are leaning towards more AI optimist kind of position, where we hope that we can build open source models, democratize AI, and make AI field work for humanity without having to overly constrain that development. So walking the line and figuring out the balance is, of course, critical. But I just want to quote my favorite short sci-fi story, Gentle Seduction by Mark Sigler. You can Google it. The bottom line of that story is, when different civilizations in the universe were going through singularity, some indeed went too fast, too careless, bad things happened. But some went to the other extreme. And they were so consumed by fear that they constrained their progress, and nothing good came out of that. And only those who proceeded with caution but without fear survived. And I think that's what we should do. Since, yeah.
Very much. Irina Rish. And we